So I've just put here the dx, how the distances and how the projection is for your understanding while we're going and we're basically coding this in order for you to have that ability. And one other thing that is important, there's also Rodriguez rotation that I've created there. That also has to be copied here, and I'm going to show when it would be utilized. ICP registration, and this is our plane model, so the STL, using the STL file format rather than just a set of points that are random and arbitrary. We had the X of scan, we had our STL. Now this time we don't have the X of BIM, we have to create the X of BIM. So we have to create another program in order for us to perform that. So this time we have the STL and we have the X of scan. The outputs are quite similar. We have that distance that we needed for the heat map. We have the correspondences, and we have the rotation and translation and the RMSE. We actually also output the X of BIM as well, just for practicality purposes. And the distance from point cloud to your model, and this is essentially your STL, your heat map that we talked about it in the previous one, and the RMSE. Of the registration. So the next part is the thresholds, and we again have the same two thresholds. We have a threshold for the distance, and we have a threshold which is representing which closest elements you actually get from every point cloud. And we have the second part, which is your RMSE threshold. And this is the RMSE threshold between consecutive iterations. Okay. So the first part that we have to do, reading the STL file format. Yeah. And this is basically what we talked about here. We just copy that there in our code. And just for practicality, we just put it in the function there for simplicity. And this is the area, as I said, is going to be used for object detection later on. In the next session, we're going to go through that. Treat it next session. Okay. So we have the attributes, we have the bounds, we have the area. Okay, so for each and every one of these, we need to find, and we have the boundary of that particular object. For each and every one of these, we need to find basically what points are first closest to it. And then once we found the closest plane, then we have to find which one is within the boundaries, right? So we have to use those attributes and boundaries. That's all. So the second one, or our second point, is finding the closest planes to every point that we have, or STL surface. And after we treat it this way, it's going to be planes for each point cloud. Okay. So for this, we need to first find the distance of basically every point from this, the attributes that we've had, which is basically this equation. So the first one is finding the distance. Then we have to check the distance Then we have to find the projection. Then once we have the projection, we can now say, check whether it's within or outside. Okay, so let's calculate the distance. So we have the x of scan of r, okay, that's going to be a row vector. So it's going to be an eta that we have is this way. So it's going to be eta prime, right? Because instead of having it as a column vector, we're having it as a row vector. We have a row vector, and then we have the attributes, which are the eta. It used to be a row vector. We now have it as a column vector. And now we have to also add one set of ones beside our scan, because it's going to be x, y, z, and the ones, right? So we first size our x of scan of r, and then we basically put a set of r as a column with the same size of the rows as our x of scan, and times our attributes prime, which is basically the transpose of all of these, because it's going to be this transpose times this, right? This times this transpose would be this transpose times this. Okay, so let's see how it looks. Oh, I cleared the x underline r. So if you scan r, if you don't have it, then you just put it by means of the scan r2, and you put it there. So now you basically copy, and now you have the attributes. So the attributes, or sorry, the distance. The distance shows the distance of every point in the point cloud from each of the planes. So every column represents a plane. Okay, so this shows that the distance of the first point cloud in your scan R from the first surface. The second column shows the distance of the point cloud from the second surface, the third surface, the fourth, fifth, and sixth. And this is, of course, you have minus and positives there that you're going to use in this formulation there. But at the end, the absolute value of this distance has to be less than the distance threshold. Some of these points do not have that. Some of them do have that. But the ones that do have that, we find the minimum of that. And once we do find the minimum of that, then we'll basically going to go project that onto it. Once we project, we have to find whether it's within the bounds or not. Okay. So let's go the second part of that. So we need to check two items. The first is whether it's within, or which one of these are within the distance threshold, or let's say the minimum of this if it's within the distance threshold. And that's what we go about in order to not perform this multiple times for multiple of them that might be within the distance threshold. If the distance threshold is smaller, if the distance is smaller than the threshold, okay. So for this, we find whether the minimum of every row is actually smaller than the distance threshold. So for this, we actually perform what we call a for loop, right? So imagine for your distance, for your if iteration, or for your if element, let's calculate this together. So for the if point, what we do is we basically say, okay, the distance of the if row and each and every one of this, we find the minimum of that. So we get the absolute value of the distance of the if row and all of the other ones. We find the minimum of that. And this minimum, we're basically simplifying the equation a bit. We're basically saying if this minimum is within the threshold that we set there, then we go and check to see if it's within the boundaries or not. Okay, so the first point is, let's say DL, this is when you put the minimum function, the first one gives you the minimum of that particular set of arrays or specific vectors. The second gives you the index. So if you have the distance of 1 and let's say 1 to 6, if there's a minimum there on 4, on the fourth column, and it's, let's say, is 0.02, the DL would give you 0.02, and the IL would give you the 4, which is the column representing that. This is going to be useful because we're going to utilize that. Okay? So then here we have to have an if statement. We have to say, if our DL is smaller than or equal to our distance threshold, then we go to the next step. And what is that next step? To check to see if this is within the boundaries or not. Essentially, if we project this point onto it, so instead of us projecting it on all of these planes, we basically simplify it. We do it on the closest one. If it's within it, we select it. If it's not, we go to the next point. It's like, it's within the boundaries or not. And for this, we have to use a few different functions that exist for MATLAB. And of course, the Rodriguez function for rotation that I've created as well. So the projection, we use this formula, which is our x, which is the x underline scan r of I and the rest of the columns, minus the distance that we have here. But the distance is what? Is going to be distance of I and IL, or you can use DL here. It's the exact same. Actually, no, you can't use the DL. I apologize, because you're using the absolute here. So you have to use the distance of I and IL. But magnitude-wise, they're the same. The minus and positive impacts how this function actually works. And once you have that, the distance, then you multiply it by the normal, which is the first 3 columns of your attribute. So the attribute is what? The attribute is the attribute of IL, because that was the column, right? That is the row of the attributes, and then the first, second, and third column for that. And this would give you the projection. So once you have the projection, now this projection is in 3D. You know, sometimes the planes are not exactly here. They might be, let's say, tilted. So you need to find where that boundary is. You have the boundary. You need to find whether it's inside of it or not. And there are methods to do that. But MATLAB has a good, efficient algorithm for doing it if you have it in 2D. So what I propose and what I typically do is that I get that normal vector that we have, which is the attributes of IL and 1 to 3. I basically rotate that so that it is straight to the z-axis. What ends up happening is now whatever point or projection I have is in the xy plane. So if I use only x and the y coordinates, okay, and completely forget about the z, that is going to be the exact same process that we're going to use. And we can use now the MATLAB's 2D version of finding whether a point is inside of a polygon or not. So the first thing that we have to do is we have to find a rotation that takes the normal vector, which is the attribute here, okay, onto 0, 0, 1. And once we have that, now we can work on the xy plane, basically what is there. And so we rotate then our projection, and we rotate the box, the boundary that we get, that the boundary, we rotate it, and then we only use the xy plane, and then we use MATLAB's formulation to find whether it's inside or not. Okay, so how do we do that? So this is calculate the projection of that point. We found that. Now if we rotate the plane such that the normal is in 0, 0, 1, now we can work on the xy plane. Direction. or let's say parallel to the z-axis, then our plane is exactly the same plane as the xy, right? It's clear, right? And MATLAB has a good algorithm efficient for that, so we don't need to create something new, which is not something that I would like to do because it digresses from our actual work, which is exactly this. Has a function basically to check whether it's within that or not. Okay, so let's go for the 2D for a polygon. So rotation, we gave that Rodriguez rotation. That's the function that I have created. I've used it throughout my thesis, throughout my papers. What it is that whatever vector you have, as long as it's a normal vector, or basically it's normalized, you can put the first vector and you can put your final vector that you wanted to rotate to, and it gives you the rotation right there and there. It's using the formulation created by scientists called Rodriguez. Basically, I put it into a formulation there. Take it from there. So what we have is we have rotation, Rodriguez, attributes of IL and 1 to 3. It goes to 0, 0, 1. Okay. Once it goes to 0, 0, 1, this is the estimated rotation. We just multiply that approach, which is the projected, to the 0, 0, 1, and use only the x and the y, the first and the second. We do the same thing for your boundary as well. Basically, the bounds there, you have the bounds of IL, okay, and 1, that's the cell array, and you basically use that, and you multiply it by the rotation. So we do project of rotation. This is equal to your projection times your rotation. Okay. And then you do the exact same for the boundaries. So let's call it box. This is going to be the bounds, but this bounds here, which is here, these guys, it's going to be, so I don't know if you know, these are the brackets, not the actual bracket or parentheses. It's those particular brackets that you use, and this is for cell arrays. So just keep that in mind. It's going to be IL and 1. IL is because we found IL as being the one that is the closest, right? And it's within the boundaries that we have. Times rotation. Now what ends up happening is if we use the first item and the second element in columns for projection of row and for the box, what it gives us is in 2D, we can find whether this point is within this or not. And MATLAB has a function for that. Rotate the boundaries and then only use the x and the y, or the first and the second. Now we can see if the point projected is within this boundary, which is box in 2D. We just completely ignore the z, right? Because now we've rotated this into it being parallel to the z-axis. So we can treat this as a 2D in xy. So the function is called inpoly. So you have the project underline rot, the first element, which is the x, and proj underline rot, which is, and the second element, which is 2, and the box, the first column of that, and the second column of that. And this function is written in MATLAB. You can go and search for that as well. And if you put in and on, it gives you a bunch of logicals, meaning if it's in, the in would be 1. If it's on, meaning on that boundaries, it's going to, on would be 1. If both of these are 0, it's going to be outside. So if in or on is a logical, if these two are equal to 1, the point is going to be either on, or how I said it here, the point is not, it's not outside of this boundary. So you would pick that point as a point that is corresponding to your point cloud. Okay, so we write this: if in equal to 1, or basically 2 lines here, on equal to 1, then your x underline BIM of I, which is the ith element there that we're basically treating here, because we did it here as well, is equal to the proj, this proj that we get here. Okay, else we have to now create an ID in case it is not the same, right? So we say ID of BIM is going to be of I and 1 is equal to, let's say, 0 or 1. It doesn't matter. Let's say 1. And then here we have to create an ID of BIM that has all zeros. And the ones that are 1 are the ones that did not satisfy this condition, meaning that we can rest assured that this point is actually outside. So if this equals to 1, that means that this point is outside. So for that particular point of the point cloud, there's no correspondences that are closer than that threshold that are within the boundaries of a surface that we have in the BIM. So we cannot create a correspondence there. This is important because this is going to be utilized for that. And then at the exact same time, if this DL, meaning that we have no planes that are within this threshold, this again has the same circumstance. So again, we have to copy and paste this here. If there's no planes that are within that threshold that we want, is going to create the same circumstances. Okay. Now, these are all, this is for the ith point. Okay, this is for I equal to 1 or whatever. Okay, all of these can go into what we call a for loop. So for every point, this needs to happen. So let's go where I equal to 1 and let's see how it is. So let's copy and paste it there. So you have the DL, you have the IL. The DL was 0.0. So this is the minimum because we found the minimum of the absolute 0.0395. And this 0.0395 is actually smaller than your distance threshold. Okay. And IL is basically the 5th element. So IL actually is 5. So that's how that is represented. Once you have that, then you check if DL is smaller than this. This is smaller than that. We check that there. So let's take a look at the rest of these. And let's copy and paste this. Yeah, from there to the in. And of course, if you take a look at it bit by bit, it makes sense, right? We calculate the distance, we find what the closest distance is, we project it on top of it, and then we compare to see if it is within it or not. And let's enter this. And once we press enter here, what we get is in and on. So the in and on are both 0. That means that whatever projection points we had from the closest surface was not inside of that surface. Okay, so let's take a look and see how that looks. So let's go PC show of our first element, which is our X underline scan R of 1 and or I, and because we put I as 1. So it's this small point here. I don't know if you guys can see it. I'm going to show it here. It's there. And then let's hold this. And let's now put the tri-surf there as well. Let's put the tri-surf there of TR. So we can compare them together and see how it is. Okay. So as you can see here, this small dot here, this is what we're talking about. But I'm going to zoom in on it. Go here and let's just change it to a more pronounced color, let's say red. And if you see this here, this is clearly not within the boundaries of the STL, and the program has correctly identified that. If you go around, this is basically the surface here, the side one there. That is the one that is the closest to this point, because this point, if you get the distance here, is the closest. That's why the distance by itself is not sufficient, right? Because this distance was still less than the threshold, but it was clearly outside of it. That's why we had to do all of this. And then, of course, when we do this, then if we copy and paste this here, the ID underline BIM 1 should be equal to 1, which it is. That means that this ID underline BIM is not a BIM that we're going to be using. And the X underline BIM is not existing. So this is for the if element. So we want to do it for I equal to 1 up until the n, right? So we basically put that into that loop. And that loop is called a for loop. When we know how many iterations we're going to go, for loop is a pretty good solution. We can still create it with a while loop. However, this is the best. So let's just put it that way. We say for I equal 1 to n. N is here the size of our XR. For every row, we perform these tasks one by one. And then we put end at the very end here. And what I wanted to do is I wanted to basically put this into a function, because it's just simpler for us to put it into a function here. Of course, from the top here, from the attributes. And it's in good form, especially when we know how many of these elements are. It's in good form to always put them and place them as what they are. So it's in good practice to say, okay, the size of the X underline BIM originally is going to be the size of the X underline scan R. So we basically populate it with a bunch of zeros. And then the same with the ID underline BIM. And then how we find which one are the best is the ones that the ID underline BIM is equal to 0. Okay, so we say X underline BIM is zeros of n and 3. That's exactly the same as the size of the X underline scan R. However, we populate it with zeros, and then we put them into this as long as they satisfy this condition. And the ID underline BIM, let's put it zeros of n and 1, because there's a bunch of IDs, logical. And then if they are 0, then they are the points that we are wanting to compare together. And let's just copy and paste this into our program. Okay, and let's run it. And it goes a few seconds. And then it gives you basically what you have, which is the ID of BIM. Essentially, the ID equals 0 are the ones that we want to extract from that. And that is exactly what we want. So let's see the point cloud that is created by that. And this is exactly what it is. So let's say PC show X underline BIM of ID underline BIM equals 0. That is the only ones that we want. So this is how we show it, underline BIM equals 0. And the rest of the columns. And you enter that. And what you get is this. And this is essentially what we have here as our representation of the points on the BIM that represent the points that are closest in the point cloud. Okay. And this is what we have here. Okay. Now let's make it into a function. So BIM simulation underline STL. So let's create a new script. And let's say BIM simulation underline STL. It takes the X of scan R and it takes your STL. And what it gives you is your final X of BIM. Attributes and bounds, that's totally fine as well. If you don't want to put this here, but you could put it there and say STL, that's totally fine as well. And then you don't need to put the STL in the other one. You just basically use it as a function there. Okay, so this is your function. Save it as the function BIM simulation STL. And that means that given your X underline scan, your attribute, oh, this also requires the distance underline threshold as well. So as your input. So what it gives you as output is X. So then once you have that, you can now utilize that with respect to the ICP that you have here. So you don't need to paste it, but I'm just showing that you see in the ICP, you had the X of BIM, distance, all these types of things. You basically have to utilize that same procedure here. So for this, again, one thing that you have to keep in mind, so you basically bring all of these back down there. All of different steps that are required. And where you're required to add that XBIM and IDBIM is down when you want to perform the rigid body transformation. So you basically don't need those aspects. You really don't need the finding the nearest neighbor because we already did that. And it's surprising because when you perform it in the way that we have performed this, because it goes around performing it in a nearest neighbor search, we're much more advanced in how we can handle it. So here we basically copy what we had there, and we have the X of, and instead of the ID, we basically put ID underline BIM equal to 1, but I'm going to fix that later on so that we can make it nice and tidy in ID underline BIM. And this is again ID underline BIM. They're the same size this time, purposefully without any problems. And the rest is exactly the same. So we just need to bring this here down before the rigid body transformation. Paste it here. Okay. We just change it to 3, 4, and the rest. And basically what we get is this. At the very beginning, we can basically put this as a function. Now we can define that function. And we can, of course, end this and also put the distance there that we wanted, that we were very, very much interested in as a distance function. And for that, we can just create that distance. So for that, we're going to have our X underline BIM ID. And we're going to basically put X underline BIM of ID underline BIM. But for the first 1 to 3, so all of the columns, okay, minus our X underline scan of R of ID underline BIM. And what we wanted to do is we wanted to power it to 2, sum up the horizontal, and square root that, right? So we perform that and put dot to the power of 2, that is elemental, then sum it up, and we have to put 2 at the very bottom because that is horizontal. And then you square root that. Okay. So this is going to be your distance. Now your function is what? Let's just copy this just to kind of be a bit more consistent there. Paste there, and let's say scan R. But here, instead of LD, we have ID underline BIM. And for dist, distance here, we have the distance, and we just change this instead of the point to point into the STL, but here we just need to put this as, let's say, STL. And we need to put, instead of the X underline BIM, we put STL. And instead of ICP point to point, we can put function. Instead of ICP point to point, we basically put point STL. That's pretty much it. And here we observe that, for instance, that this underline fresh was not utilized, but that had to be utilized in the BIM underline simulation. So I want you guys to open this up again. This is how you can, of course, risk manage and make sure that these types of variables are always going to be utilized within yours. So just at the very end, because we've introduced that here, right? So we basically put that as an input there, this underline fresh. Okay, so this is in your BIM simulation underline STL. And then if you go and run this, what ends up happening is that this ID is not going to be correct because the ID is 0 or 1. So you had to put ID underline BIM of equal to 0. It is easier to perform that if we can perform this in terms of, how can I say this? If we can perform this in this terms. So if we can go and basically go to the line here, okay, either we can do this ID of BIM equals 0, or we can go to the BIM simulation. I'm just giving you some pointers of how you can perform this. We can, these are ID of BIM equals 0 are the ones that we want that have some value. So we can just change this ID underline BIM into ID underline BIM of, or find ID underline BIM equal to 0. And that would give you all of the rows. So you basically change that and you don't need to change the rest of the algorithm based on that. And it's much more efficient. But you could have performed exactly the same. You could put each and every one of those that. But what this does is it says it finds all of the rows or the indices of the rows that represent ID underline BIM equal to 0. You save this. So let's now copy and paste this. Okay. And once you copy and paste this, then you get your RMSE, you get the XBIM, you get all of these aspects. So let's PC show our X underline scan our this is the whole overall. The X underline scan R of ID of BIM. That is basically what we want. Underline BIM. Okay. And the dist, which is the distance there, that is that heat map that we created. And this provides you with that heat map that we want. As you can see, it's much more, much better in comparison to the other one, which was a bit more roughed up around the edges. But you still see that these points are selected, and because we have no other means of selecting but the basic points there. Okay. So we hold this and we do the try surf TR to kind of see how close they are. Let's go with the view of 90 and let's just change this into like white, just to kind of give a bit of an idea. Now let's go to the 90 degrees there, view 90, minus 90 and 0. Let's see how this is. If you go in 19.0, we're going to see this. And it looks like it's pretty much the best that you can get with respect to the data, given the fact that these two data are not fitting properly and correctly and completely.